In this lecture, we will derive the field at a remote point due to a magnetic dipole, and we will also calculate the vector potential. Let us say that there is this circular current carrying loop. Now, we want to find the field as well as vector potential due to this current carrying loop at a point P which is very far. Let us say this is x axis, this is y axis, and this is z axis, and it is carrying current I, and let us say its radius is b. Now we want to find the field, let us say at this point P which is very far from this magnetic dipole, and since you know that at this remote point the field will not depend on phi, as far as this distance from the center is equal, then this is not going to depend on phi. So for the ease of calculation we will take phi is equal to pi by 2. What does it mean? It means that this angle is pi by 2, that is the point is in this yz plane. So this point is at, from this is the origin of spherical coordinate system, r theta phi is equal to pi by 2. So this is r. Now this is in yz plane, we should remember. Now for this yz plane you will find that a phi, the vector a phi, is simply equal to minus of ax. If this is ax, this is ay, then a phi will be like this. If you want to see it, then it will be totally opposing this, like in this direction. So it will be like this, means in minus of ax direction, this a phi vector. You should try to imagine it, and if you don't are not able to imagine it, I suggest you watch my lectures on curvilinear coordinate system, that is both cylindrical as well as spherical coordinate system. Now since this point P is very far away, then we can make some simplifying assumptions, and we can also see that the shape of this current carrying loop doesn't matter much. It can also be a square, but for the ease of calculation we are taking it as a circular loop. Now a is equal to mu naught I over 4 pi dl dash over the distance from the source to the observation point. So for our case, let us take this small element dl dash at phi. This is angle phi. Let us say the projection of this point P on y axis is P double dash. So this point is this will be r1. So here this is r1. Now we need to convert this r1 to somehow this r, so that we can generalize our formula. So for our case, dl dash is equal to a phi b d phi dash. Now you should try to imagine that this a phi here is not equal to a phi here. Here a phi is equal to minus ax, but at this place a phi is actually equal to minus ax sin phi plus ay cos phi. So you see, if I put phi is equal to pi by 2, then you can clearly see the a phi is equal to minus ax. So for this, we are sure that it is minus ax. But here, a phi is this. So dl dash can be written as minus ax sin phi plus ay cos phi into b d phi dash. So we have found the small dl dash here. Now why we needed to convert this into x and y? Because you know these ax and ay are not going to change. Since you can see that a phi was going to change at both point, so it would be very difficult to find the integral. So to ease our calculation, we have converted into the Cartesian coordinate system. Now you will see that for further easing our calculation, we can see that for every current carrying component here, dl dash, idl dash, there will be a symmetrically placed dl dash here opposite to this or across this y axis, which will be contributing to a in minus ax direction, but they will be cancelling the contribution in the y-axis direction. So you see that this a will be giving in this y direction this component, and this direction this component. Similarly, this a will be giving in this y direction and in this direction ax. So you see that both of these current carrying element are contributing in ax direction, but their contribution in ay direction are cancelling each other. So we do not need to calculate this part. We need to calculate only this part. So again, we have further, made our calculation easier. So now we will turn to do the calculations after we have, simplified our problem. So A is equal to minus AX mu naught upon 4 pi I 0 to 2 pi B sin phi d phi dash over r1. Now we need to somehow change this r1 to r, so we will see how to do that a little while later. Now you see this minus ax is actually equal to a phi at the observation point, and we are calculating a at the observation point only. ib sin phi d phi dash r1 from 0 to 2 pi. Now in this triangle O sorry, let us say this point is P dash. In triangle OP dash P, so in triangle this OP dash P, we can use the law of cosines. So in this triangle, if I use the law of cosines, you will see that this r1 square is equal to this r square plus this b square minus twice of br and the angle between them, cos, and let us say this angle is psi, 2br cos psi. So we will use this law of cosines in our calculation. So r1 square is equal to r square plus b square minus 2br cos psi. Now we have some ray of hope that we can replace r1 somehow with r. Now you will find that r cos psi, what it is. R cos psi is the projection of R on this radius OP. R cos psi is the projection of this R on this radius OP dash. Okay. So now this OP dash, this projection on OP dash is same as that of this projection OP double dash on OP dash. That is, this projection on OP dash is same as this projection on OP dash. So I can write R1 square is equal to R square plus B square minus 2B. Now this is the projection of OP double dash on OP dash. R sine theta sine phi dash, where theta is this angle is theta. So r sine theta will be this OP double dash, and its projection on OP dash will be same as the projection of r on OP dash. Okay, so that's why we have taken this projection r sine theta and its projection on OP dash. This is phi dash. If it is phi dash, this angle is phi dash, then it will be 90 minus phi dash. So projection will be cos of 90 minus phi dash is equal to sine phi dash. So that's why this is the projection here, r sine theta sine phi dash. So in this way we are successful to somehow convert it into still r and b only. So 1 by r1 square will be equal to 1 by r, I am just taking it inverse, 1 plus b square r square minus 2b r sine theta sine phi dash, just 1 by r, I will take under root here, minus 1 by 2. Okay, so now since r square is greater than b square, so this b square by r square can be neglected in comparison to this one and this. So 1 by r1 is simply now approximately equal to 1 by r 1 minus 2b by r sine theta sine phi dash raised to power minus 1 by 2, or by further expansion it will be 1 plus b by r sine theta sine phi dash. So a will be simply equal to a phi mu naught I over 2 pi r b, and phi varying from d phi varying from minus pi by 2 to pi by 2, 1 plus b by r sine theta sine phi dash sine phi dash d phi dash. So we can easily now solve this integral. It is very easy to solve. On solving, we will find that a is equal to a phi mu naught I b square over 4 r square sine theta, or we can further resolve it. A is equal to a phi mu naught I pi b square over 4 pi r square sine theta. Now if this is z axis and if this is angle theta, so this Sin theta will be az dot ar. Okay, so a is equal to a phi mu naught. This is equal to simply the magnitude of the magnetic dipole moment over 4 pi r square sin theta, or a phi mu naught m dot az 4 pi r square. This is capital R. uh, Sorry, this is will be az cross r will be equal to sin theta. If this is theta and this is ar, so az cross r will be sin theta, and az dot ar will be equal to cos theta. So I did small mistake. It will not be dot product, it will be cross product, and it will be m is in z direction, so I have taken it here. So m is actually m az, and its cross r will give us m sin theta, and direction of z cross r is simply in phi direction. So in this way I don't need now phi here. So you see that a in vector form is simply mu naught upon 4 pi r square m cross ar. So this is the vector potential due to a magnetic dipole at a very far away point. So on comparison, you can see that for scalar potential for a electric dipole, it was m or p dot ar over 4 pi epsilon naught r square. So the format is similar, only the dot product is replaced with the cross product. Okay, and 1 pi epsilon naught is replaced with mu naught. So somehow the expressions are quite similar in form. Okay, if we just see this replacement. Now from this we need to find the magnetic field. So we have found that A is equal to a phi mu naught I b square 4r square sin theta. So B is equal to del cross A. Okay, so in spherical coordinate I can find the curl by that general equation which we have seen in our previous lectures, and on solving we will find that B is equal to mu naught I b square 4r cube 2 cos theta ar plus sin theta a theta. Sorry, a theta, not phi. Okay, so on comparison, the electric field due to this electric dipole was uh, let me just remember it or see it. For electric dipole, the field was similar. It was having p over 4 pi r cube 2 cos theta ar plus sin theta a theta. As far as I remember, this was the field due to a dipole, electric dipole. So it is similar. If I multiply and divide with pi, I am having same form, mu naught upon 4 pi r cube m 2 cos theta ar plus sin theta a theta. So forms are similar for both the cases. So what does it show? It shows that the field lines due to a magnetic dipole and an electric dipole At a faraway point, P will appear similar. Let us see how. So you see field lines will be like this, going like this. So at a faraway point P, let us say like this, field line will appear like this. So for our magnetic dipole case, field line will be, if it is, let us say, dot and it is cross, that is current is like this, then field lines will be like this. And for field faraway point, on the axis it will be like this, and for faraway point it will be like this. So you see, for faraway point the field lines are quite similar in shape. That's why the expressions are totally same. If I just replace P or M and 1 by epsilon naught with mu naught, so that's why both of the expressions are very same or similar. Because the field lines will also appear similar at a faraway point, we will not be able to discriminate whether it is because of a magnetic dipole or a electric dipole as far as the feature of the field lines are concerned at this point P. Now furthermore, I need to verify one more thing, that this B, when we calculated on the axis of this circular loop, it came out to be, if I remember it correctly, B was equal to mu naught I B square to R cube. Okay, so for this case, theta will be equal to 0. So if I put theta is equal to 0 in this equation, I will have B is equal to mu naught I B square over R cube for twice of AR. Now when theta is equal to 0, when this theta is equal to 0, so AR is actually equal to AZ only. So I can write it as AZ. So you see, both of these equations are giving same. So in this way we can see that this equation for a faraway point is more general equation, and we will use it whenever we need to calculate field at a faraway point for the magnetic dipole. So to make it more clear, I will write it again. B is equal to mu naught upon 4 pi R cube, that is, it will fall with R cube, similar to that electric dipole, M 2 cos theta AR plus sin theta A theta, and A will be mu naught upon 4 pi R square, similar to the potential in this scalar dipole, electric dipole, it was falling with R square. Here also it is falling with R square. Only the difference is this cross product. Okay, and units are Weber per meter, and its unit is Tesla. So although this derivation was quite long, but I hope if you watch this video again and again, you will be able to clarify all your doubts, and you will be able to understand the derivation and understand the field of a magnetic dipole. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group, whose link is given in the description of this video. Thank you.